having this honor due to seniority, which is, well, only following Professor Reed, since our colleague Herb Clements left. I think I would like to...
Elton is 2 or 3 years older than
No,
No.
he's younger. I've investigated this.
you. All right, okay.
So it's a pleasure to express the thanks of everybody to the organizers for this very, and especially to the local hard-working organizers, Professor Youngnami and Bach, and also nice Reed, of course, but for organizing this workshop, which has been very lively and exciting. So I would like to invite everybody to thank the organizers. And since I did not already yet give my talk, I also want to like to thank the speakers for their excellent talks. Okay, so
Audience for the excellent listening.
okay, it's good this you can do in the end. Okay, so I should apologize that I could not, because of jet lag, fully prepare my talk, in the sense that I have too many things to say, and it's a little parties in there, parties here. So I hope, at least I want to start, follow the example of morning lectures and try to go not so quickly. So first I want to discuss the main one motivation. It's not the only motivation, and it is the singularities of the moduli space of curves, and in particular the compactified modular space of curves. So if you cannot read, or there is something which I do not define, please interrupt me and I will try to answer. Okay, so to be short, I write the singularities, but also somehow what I say concerns also the topology of the moduli space of curves, but I don't want to get involved so much. So I have, my point of view is more complex analytic, so I want to define Teichmüller space. So I want now to describe that the moduli space of curves is the quotient of Teichmüller space under the mapping class group G, which I will also denote by gamma G. So for the case of curves, you have a global orbifold structure. So let me recall these definitions. So I take mg is this infinity Riemann surface compact of genus G. And
Why do you call it sigma?
because it's a manifold. Usually I have, I'm very lazy, and so usually it should remind me. Okay, so it's a manifold, and in general, now you look at the C of M, also C stays for complex, is the space of complex structures. And, of course, you can act with a group of diffeomorphisms. These are infinity complex structures, and one defines the mapping class group is just the group of orientation diff plus of M. So plus means that these diffeomorphisms are orientation preserving, modulo the subgroup of diffeomorphism which are isotopic to the identity. So I take in this infinite dimensional group, I take the connected component of the identity, and then I take this quotient here. And okay, I will later explain what is more concrete in the Mac-Linkers group. And the Teichmüller space is just the space of complex structure divided by the action of diff 0. And so the moduli space is obtained by dividing by all the possible diffeomorphisms. Therefore, it follows that Mg is the Teichmüller space divided by the quotient group. Now, okay, this you can do for any complex, compact complex manifold. But up to now, these are only topological spaces. However, there is a theorem. Let's see how we want to see. Maybe since a theorem here is that at the point corresponding to a complex structure C, Teichmüller space is homeomorphic, is locally homomorphic to the Kuranishi family of the base of the Kuranishi family of C. So you take the deformations, the Kuranishi, and this is locally biholomorphic to C to the 3G minus 3, assume that G is at least 2, and hence TG is a complex structure, so hence TG is a complex manifold. And in fact, it is known more, indeed, TG is biholomorphic to an open set in C to the 3G minus 3 and gamma G acts properly discontinuously. Okay. So this shows that we get a quotient of a complex manifold by this, and so locally and similarly we have the theorem that also Mg bar is locally biholomorphic to the quotient of the Kuranishi.
Mg, yeah. There is no bar yet.
Then this is a new theorem. Okay? The first theorem was for Mg. Similarly, there is another theorem from Mg bar says that Mg bar is locally biholomorphic to the quotient of the Kuranishi family of G by the group of automorphisms of C. And where out C is a finite group. And Kuranishi, also for moduli stable curves, the Kuranishi family is smooth. So locally, the moduli space and the compactified moduli space are the quotient of a manifold by a finite group. And therefore, the singular, from this it follows that the singular locus of mg bar can be now described in terms of curves with automorphisms. So corollary, the singular locus of mg bar corresponds to the curves such that now the automorphism group this automorphism group X on the Kuranishi family has image not generated by pseudo-reflection. So it's a theorem of Chevalier and Shepherd and Todd that this is the only. Now, what is a pseudo-reflection? I think everybody knows, but a finite group can be linearized if it has a finite point of the origin by result of Cartan, and the pseudo-reflection corresponds to a matrix, diagonal matrix with all eigenvalues 1 and a root of unity. So in particular, if there are pseudo-reflections, this means that there is an automorphism which has a divisorial fixed part on the Kuranishi space. And so there are two examples. So to this regard. So there is one case for G at least 2. So if C has genus 2 and sigma is the hyperelliptic involution, then of course sigma acts trivially. So I made a mistake here. Yes? On the more.
So Fabrizio, Kuranishi space is a germ of a complex manifold, so you can't write C. You mean the germ of C3 minus G at the origin?
Right.
On the next line. Germ. Yeah.
Yes.
Yeah.
Of course. I tend to leave something, maybe more than one. Okay, but you're right. This is a germ, and it's linearized, and then so here all the curves of genus 2 have the hyperelliptic involution. So let's forget about that. And the only pseudo-reflection is given by the curves of genus 3 and sigma, which is again hyperelliptic involution. And so here you have a divisor, and in M3, and a pseudo-reflection, and the reflection. So for MG, these are the only exceptional cases. For MG bar, the story is more complicated. Okay, so of course this motivates the study of automorphism of smooth curves. So let me first do this by curves. So chapter 2, automorphism. And let me restrict to G at least 2. Now, the main point is that the automorphism of a curve of genus 2 cannot be isotopic to the identity. And simply because the number of fixed points is negative by the Lefschetz fixed point, by the intersection number of the diagonal with the graph. So, and that's the reason why you see. So it turns out that if G is contained in the automorphous group of C, and this means that the automorphous group of C, this is just a stabilizer of the point C in the mapping class group. And so you see that an action, so composing these inclusions, so in general a topological and admissible topological action means that I have rho, a homomorphism of G in the mapping class group. Well, modulo automorphism of G. You can always compose with an automorphism of G. And now the main point is that since the main point is that my MG has a universal cover which is contractible, so KG is a classifying space for the group PG, which is the fundamental group of KG. So this is an Eilenberg-MacLane space, and from this it follows that well, this action is completely determined by the action on the fundamental group, but inner automorphisms are isotopic to the identity. And so it follows from this description, there is theorem of topology here, map G is just the group of outer automorphisms of G, which is the automorphism, of pi G, the automorphism of pi G modulo inner automorphism. So this shows that there are several definitions, but they are equivalent. So the mapping class group is also, for algebraists, the group of outer automorphisms of this group pi G, which is the fundamental group of the Riemann surface of genus G. Okay, so let me mention now the first theorem, which is the first one in the series, so theorem 1, is that if I look T, G, capital G, rho, the set of curves, you can say it now in two ways, so I will only write that C is stabilizer, is fixed by rho of G. Okay, so you have a fixed locus for this action, but these are precisely the curves which admit an action of the group G as a group of automorphisms with the given topological type rho. What can we say about this? And then it's a beautiful result, is a connected complex manifold homeomorphic to a ball. So actually this was a proposition in a paper of mine which appeared in American Journal of Mathematics, but later on I observed that it had not been pointed out anywhere. And the proof is just follows from Morse theory. And of course, I mean, I did just a remark. The hard work was done by Tromba and others in they showed that there exists a G-invariant exhaustion function which is convex. So anyhow, so this is important, so that this locus is connected, so it gives more than irreducible complex manifold. And
so if G is nothing,
pardon?
If G is nothing, this proves that
yes,
it goes back to
perfect, exactly. So it's really the same proof, the same argument. If G is the identity, more than nothing, it proves exactly that it reproves. Yeah.
Yeah.
So in fact, they proved. I mean, you're right. Tromba gave a proof that Teichmüller space is homomorphic to a ball by constructing this exhaustion, and then, well, doing everything G-invariant, you just get for free the same result, well, which is quite interesting for topology. Now, how do we understand, I mean, as algebraic geometers, we want to understand what is this rho, okay? So, so the algebraic geometry point of view, so we have assumed that G X on C. And so these are holomorphic, automorphic, so we have a projection map. C goes to C modulo G, which will be denoted by C prime. So I want to produce some invariants of this action. And the first invariant, so pi is the projection, so invariants are G prime, which is the genus of the quotient. Then I have and then I have the number of branch points, and then I have the branch locus, P1, PH. Now conversely, and then I have a monodromy homomorphism from the fundamental group of C prime minus the branch locus onto G. So this is the algebra geometrical point of view. From the Riemann existence theorem, if you give a curve and a point and a surjective homomorphism, then you recover a covenant. Yeah, so what is the relation with the previous point of view? So I want now to describe the relation between the monodromy mu and rho. So now I have this curve here, C prime. Maybe I do the picture here, because even if you don't see it so well, so you have C prime, and you have this handles, and then I will have these branch points which I can put in a disk. And in this situation you have you take a base point and you take a fundamental group. Generators a fundamental group like this, and well, so my fundamental group here is generated by alpha 1, beta 1, alpha g prime, beta g prime, gamma 1, gamma h, and you have the relation that gamma 1, gamma h times the product of the commutators of alpha I, beta I is 1. And let me call this pi g prime h. And then you see that actually what matters is the class. Let me write it a little bit better. Okay, so yeah, let me state it already as a theorem. So so we have pi g prime has an epimorphism onto G. And the kernel, so now you take a quotient modulo this subgroup generated by gamma I to the mi, you take the orbifold fundamental group, and the kernel is the fundamental group of G. So if you take what is called the orbifold fundamental group M1, MH, where Mi is the order of mu of gamma I, so gamma I goes to an element here, which I call Ci. It has a certain order, so it factors this homomorphism through putting to 0, putting equal to 1 this, and the kernel is this. And now it's the theorem is that giving G rho is equivalent to giving the epimorphism of pi g h onto G modulo the action of the mapping class group G prime H. This is the mapping class group of C prime minus the branch locus. And it is, well, one direction is quite obvious, because from this sequence here, you take an element, you lift it, you make it act by conjugation on the normal subgroup. So you get an automorphism. If you change the lifting, you change by an inner automorphism. So the direction, this direction, you just let lifts of G act by conjugation. Okay, so if we fix a group and an action, we get something irreducible, and the only thing which we want to understand is the topological action, or equivalently so I forgot here also to put a modulo automorphism of G. Okay, depends whether you look at action of G with a given identification, or you can change that. And from this it follows another theorem, which is this time more well known, and is the following, is that theorem 2, this is the theorem 2, and then in this way, theorem 2 continued, part 2, is that M, the image mg, capital G rho, is a closed subvariety of mg, irreducible, of dimension equal to 3 G prime minus 3 plus H. And this follows because this set is a connected complex manifold, so its image is irreducible, and the only thing which one needs to prove is that this is closed. So this shows that if we look at curves with automorphism, somehow we understand very much the topology, because we take a ball, we divide by some action, we get these strata are closed, and they intersect if two groups are, and some actions, they are contained in a bigger group. So this looks like we are on the right path to understand everything, except that, well, one would like to understand very well how to classify the topological types. So I should say, as a motivation, that there's this theorem of Cornalba, is that the reducible components of the singular locus of Mg, they correspond to the case where G is cyclic of prime order of fixed numerical type. With some exceptions deleted. So it's rather clear that if a curve has a group of automorphisms, well, it has an automorphism. And well, it has also the power. So it can always reduce, if you want to find the largest closed sets, you reduce to the case prime. And so you list them all, except that it might happen that some component is contained in another. So I don't know, I shouldn't do this because this will spoil my lecture, but I want to give a nice example. Okay, so one exception. So you take C, so to be quick, I will describe function fields. So C of my curve is just given by X and by Z, or if you want, Z is this pth root of X minus 1, X plus 1. So we have an automorphism tau prime is of order p. And it's just multiplying z by a primitive root of a pth root of unity. This is a case which is exceptional. Why? Because I can take tau is just the involution which sends x to minus x. And so the invariant of c divided by tau are just x squared and z. Okay, so let me call it y. So this is just c of yz. On the other hand, z to the p is equal to x squared minus 1. So this is y minus 1. And so you see that y is z to the p minus 1. So this is c of z. Okay, so c divided by tau is p1, so it's hyperelliptic. So this shows that all the families with these automorphisms of order p, they are contained in the hyperelliptic locus. And Kurnalba has a very nice list of all the possible exceptions. Okay, so I want to explain what is the numerical type. The numerical type is more than the numbers which I already gave, and I hope I will leave it here because it's quite crucial. So paragraph 3 is what is the numerical type. So to do this, first of all, I let H be the subgroup generated by the stabilizers. So it's a subgroup generated by the mu of gamma I. So this is the group generated by stabilizers. So we have C, here we have C prime, which is C modulo G, and in between there is C modulo H. And this, we have a factorization, this is quite general. Every covering factors as a maximally ramified covering and an unramified covering. So this is étal, unramified, and with group G prime, G mod H. Okay, so what are the numerical invariants? So if I go back to the picture, I define this gamma I, but I could also have taken this gamma I a different way to go. So gamma I is only defined up to conjugation. So the invariance is a function ni from the set of conjugacy classes of G to N, and it just says that nu of C is the number of I such that mu of gamma I is in C. Of course, if the group is abelian, this means how many times the local monodromy is this element, but in general you take conjugacy classes. And of course, everything is modulo automorphism of G. And the second invariant That's more subtle. Is there a problem? For each conjugacy class, you look how many local monodromies are in this conjugacy class.
But what's fixed? G is fixed. G and the action on C are already fixed.
Pardon? I understand what is disturbing you. It's not this which is taking modulo G, but the function Ni is taking modulo G. Okay? So you take the class of Ni modulo the automorphism of G. First you take the conjugacy classes. Then, once you have the function, you allow automorphism of G. You don't do it, okay? And the second invariant...
Look, if I've got an element of G, it acts on a surface C, and it fixes some points with some order. Yeah, it could be...
No, an element here. You see, the only stabilizers, they lie over this point here.
I'm sorry.
And over each point there is an orbit, and so it's better to count downstairs.
So
You can also count upstairs, but...
Downstairs, above a point downstairs, there is only one behavior, one ramification
Exactly.
behavior.
Yes, that's exactly...
Okay,
That's exactly
yes,
that.
okay.
Okay? So the second invariant is more subtle, and it's topological, because now, okay, this covering here, we have mu prime from the fundamental group of C prime, which is PG prime, goes on to G, the quotient group. Now, however, C prime is a classifying space for PG prime. So I have mu prime, a continuous map, from C prime to the classifying space for the group. So a homomorphism gives a continuous map, and maybe I write the invariant here because I hope maybe not to erase it, even if I cannot promise. So to a continuous map there, so the second invariant is an element C mu in the second homology of G prime with coefficients in Z. And it's quite clear because now the second homology of C prime is generated by multiples of the fundamental class of C prime. So, and since I have orientation, I have a preferred generator, and this goes to the second homology of the classifying space, which is H2 of G prime Z. So the image of the fundamental class gives you an element here, which is the secondary invariant. So this is the first invariant, and the first invariant is the class of N. So how does this work? So let me give an example. So if the group is cyclic, then the second homology is 0. There is no such invariant. So theorem 3, if G is cyclic, then the numerical type is the class of Ni and determines an irreducible component. So in general, the question is how much, so a topological type determines a numerical type, and one asks the converse question. The answer is positive for cyclic groups, where the numerical type is just given by the number of local monodromies of a certain type. This result was proven by Kornalba in the case where n is a prime number. And the main point is that Kornalba was only using moving the points around, but not moving the curve around, which is necessary. You must use some dent twist. And essentially, Theorem 3, which I proved, I wrote down recently with a simple proof, but it also follows from Theorem 1 and some result of Nielsen describing the topological type for cyclic group. And in fact, using Theorem 1, so there is a theorem by Edmonds which says if G is abelian, then the numerical type determines the topological type, and hence, by Theorem 1, you get an irreducible component. Okay, so now there is this difficult question whether or when, given any group, the numerical type determines the topological type. So somehow this means that if I take classes, so in other words, it is convenient to look at the topological type as the quotient of these epimorphisms to the group G modulo the action of the mapping class group. And you get a mapping here to the numerical type. Which is the pair of C mu prime and the class of NIM. And the question is whether this mapping is bijective. So in the Étang case, this means that H is 0, there are no ramification points. The answer is not always positive, but there is, I want to mention a very interesting result by Dunfield and Thurston. And William Thurston. And the theorem says that if H is 0, so Gx freely, there exists a bijection between these epimorphisms of the fundamental group of a compact Riemann surface of genus G prime onto G modulo the action of the mapping class group and automorphism of G with, well, in this case there is no isotropy, so the only invariant is C mu, and the second homology group of G prime Z which indeed you should also divide by the automorphism of G prime. Okay, this result is an asymptotic result for G prime very large. So this theorem says, well, the answer is quite difficult in low genus, but when the genus becomes very high, then the number of these equivalence classes, the number of these topological types is just described by pure algebra. So it is a beautiful result. And the proof is also very simple. But it has a drawback. It doesn't tell you explicitly what is G prime. So maybe let me sketch the ideas which are lie behind the proof. And it's very simple. So the ideas...
Fabrizio, new pen.
Pardon?
New pen.
Blue or...
New.
So ideas. First idea is stabilization. Stabilization is just the trivial remark is that given a Riemann surface of a certain genus, you can always attach another. This is genus G, and this is genus H. And if you have a homomorphism here, you can extend it trivially here. So mu from pi G onto G extends trivially to a homomorphism onto G. So I don't write it, but in terms of the generators, means that if you take the alpha I and beta I, where I is bigger than G, they have trivial image. And they prove that for G large enough, and they prove that the lemma is that if G is bigger than the order of the group, everything is a stabilization. And stabilizing, so that's the first point. The second point is that stabilizing doesn't change this homology class. And there is a theorem of Livingstone is that mu and mu prime are stably equivalent if and only if C of mu is C of mu prime. And this is the trick. It's very simple, but not being a topologist, I would not have had. The main point is the idea here is that you see, you take homology of this space here, but homology is also realized by Bordism. So the idea here is that H2 of G Z is just the Bordism group of maps from a Riemann surface of dimension 2 of this classifying space. So I have two Riemann surfaces and two maps in this big classifying space. And saying that they have the same homology invariant means that there exists a three-manifold with boundary, these two, such that this extends. And now, when you look at this three-manifold, and then you look at the triangulation, this provides this stabilization result. And the third step, so this proves that, so 1 and 2 prove injectivity. Two classes inject into this, and surjectivity comes from counting, from asymptotic counting. So this is a very remarkably simple but very clever proof. And the reason why Thurston was interested is that, as you know, every three-manifold can be obtained from a Hegel splitting. And what is a Hegel splitting? You just take two handle bodies, you take, instead of taking these Riemann surfaces, you take the full handle body, and then you take another one, and then you glue the boundary with phi in the mapping class group. So studying the mapping class group is a way of describing manifolds and in a random way, and so what they wanted to see is they wanted to prove some conjecture which I will not describe, and especially show that fundamental groups of three manifolds which are hyperbolic have many surjections to finite group. Now, what is our result? So the Étale case, I should say, it's relatively easy, and the case where there are stabilizers is quite hard. So the theorem which I proved with Lerne and Perroni is, well, after the cyclic case, I take the simplest, well, it's not simple, but the least complicated non-abelian group. So for G equal dn, then the connected components correspond. So the reducible components, sorry, n G dn rho, they correspond bijectively to numerical types. And, well, this is not completely proven, so, but it's proven at least for G prime equals 0, or in the Étale case. So, of course, here you have to understand, so we give normal forms, so let me give an example. So in the Étale case, dn is the group generated by x, y squared is yx squared equal x to the n equal 1, a rotation x and the symmetry y. And in that case, the normal forms, we write the normal forms explicitly, which are y1x and then all y1, y x to the n halves, x 1, y x to the n halves, x squared, and then all 1. And this is for n odd or n even and c mu equals 0. And here is n even, so n congruent to 0 modulo 4, and n congruent to 2 modulo 4, and c mu equal 1. So this quotient of the homology group for the dihedral group for n odd is just trivial. For n even, it consists of 2 elements. So and this contradicts actually some book which I bought from Cambridge University Press. Everything is which is written about. Now, I'm just saying this because you might think that the dihedral group is trivial. Anyhow, in this book, everything which is written on the chapter of the dihedral group is wrong. And combining the case of G prime 0 with the tal case. And I stop here. Thank you.